So, welcome. Today we are going to do about defining a LeNet, and as in the earlier lecture you have already seen getting introduced to the functional blocks of how to get started with a convolutional neural network, and subsequent to that I have introduced you to some of the very basic type of architectures, and one of those predominant basic type of architecture was the LeNet, which we are doing. So, derived from the name of Jan Lecken, who started with this one. So, what we are going to do today is essentially actually go through how the network definition happens. So, you might believe that it is quite easier to get it done, because you have already learned a lot about defining networks which are fully connected in nature, in terms of your fully connected neural networks, which we done based on your autoencoders, and then autoencoders used for initializing down the rest of the networks. However, keep one thing in mind, that when we are doing convolutions, you do did get introduced onto this new kind of an operator, which was the convolutional operator, and as such the weights which are connected down are no more weights which connect down each pixel to every other neuron over there, but these now operate more of in a convolutional sense. So, there is no unique connection between a group of neurons, but they get connected via the convolutional operator over there, and that leads to even a different kind of data exchange, because while in a fully connected network your total number of input pixels was equal to the total number of neurons into the network, and then at any intermediate layer whatever is the output is the size as the number of neurons, whereas over here what happens is that there is a change over there, and in no way your number of neurons in the input layer is somewhat which is dependent on the total number of pixels in the image. So, going by that, let us get started with just trying to define the whole network first. So, the first part over here is where I will try to write down my header part. So, let us just import, and this part of my headers and all the libraries which are to be called down are in no way different, because that is quite similar to what we have done in our fully connected architectures, and that does not change anything, that does not introduce anything new as such. Going down, now comes the next point, which is trying to define the network architecture. Now, if you go by the LeNet definition and clearly recall from your slides, then you would see that what comes down over there is on the input side you have grayscale images which are handwritten digits in the range of 0 to 9, and these are encoded into small patches of size 28 cross 28. Now, these patches of size 28 cross 28 are basically what correspond to each of these ones. Now, in my LeNet, what I was doing is technically that I take down a patch of this size of 28 cross 28, and then I have a set of 6 convolutional operators. Each convolutional operator has a size of 5 cross 5. So, that is what I start by defining over here. So, you see 1 over here, which technically corresponds to the number of input channels, or how many number of gray channels are there on my input side over there. Now, my input was just a 28 cross 28 patch, and it was not a color image. So, it is just one single channel on my input what I have. So, that corresponds to this 1 which comes down over here. Now, the number of unique kernels which I am going to define and learn down in this LeNet in the first layer is what is equal to 6, and that corresponds to here, which can also be called as the number of channels in your output, or the number of unique convolution kernels which you are going to learn. And then comes down my convolution kernel size. So, my kernels over here are taken down as 5 cross 5. So, I am defining isotropic sizes over here. Now, you can also choose by defining non-isotropic sizes, and that is pretty doable, which we will be doing looking into in later on lectures as well. So, now from this what I get down is that the connections are no more NN dot linear. So, you had something like this in the earlier case, which was a NN dot linear, which is to connect down all neurons in one layer to all the neurons in the subsequent layer. Here it is not a one to one all the connections which go down, but it is more of convolutional in nature, that they are connected down, and for that reason this connection is also defined by a different kind of a function which is called as NN dot conv 2D. So, this is a convolution which will happen in the 2-dimensional space. Okay. Now, when you are doing that, you also have an option of doing strided convolutions, as well as you can do a padding in terms over there. So, over here in a standard LeNet, since we do not have the concept of padding or stride coming down in any way, so we are not going to define that. So, this is just the native straightforward definition of a LeNet as we had. The next layer over there was basically a max pooling layer which you had, and that was a max pooling of a 2 cross 2 factor over there. So, that essentially meant that you have a 2 cross 2 kernel which was max pulling it out, and you were striding it by a factor of 2. So, that meant that every 2 cross 2 2 comma 2 or 4 group of 4 pixels over there is what was represented in terms of its maximum value, and then you shift over to the next group of 4 pixels over there. So that is what we use for defining over here as kernel size of 2 and stride of 2. Okay. Now, once that is done, the next part is to go down with the next amount of convolution, and this convolution is again a 2D convolution in which we are going to connect down 6 channels of output which comes over here. Now, you can recall down from the last lecture that max pooling does not in any way do a pooling across the number of channels. So, the number of channels does not change in any way, it still remains the same. So, the number of output channels over here is still going to remain 6 after this max pooling operation in the 2D. Now, once you have max pooled out, then you have your second convolution layer or second convolution layer definition which comes down. So, the number of input channels over there is still 6 because I do not change. Now, that connects down to 16 output layers or the total number of unique kernels which I defined over here. So, there are 16 such unique convolution kernels which get defined over here, and each of the kernel has a spatial span of 5 cross 5, and that pretty much defines it. Following that, you again have a max pooling. So, my max pooling over here is again a 2 cross 2 max pooling with a stride of 2. So, that 4 pixels in a group of 2 cross 2 is what get represented in terms of the maximum value present over there. So, till here what we have is from here till here is what is just the convolution part of the definition, or within a network these are just what operate down as a convolution operation. They do not have any fully connected, or they would not be doing all to all neurons connected to each other. The next part which comes down is my first fully connected layer, and this is where it connects down 400 neurons linearly to 120 neurons. Now, the fact is, how did we get this 400 neurons? So, from the last class you do remember that we were doing a calculation of finding out exactly, like if I have a 28 cross 28 sized image which is given on an input over here, and then it does a full convolution, then you get down what do you say, max pooling on the 2D space, and then you have another convolution, and then you have another max pooling. So, at the end of the day what comes down over here is basically of the size of 16 cross 5 cross 5. So, you have 16 channels which comes down over here, and the spatial span of the resultant output over there is 5 into 5. So, that makes it 16 into 25 which is equal to 400. So, there are basically 400 such neurons present over there, but then this is a whole volume stack. So, you have the z axis where you have the different channel outputs over there, and then you have a spatial span of 5 comma 5. So, that all the neurons which is present in this whole compact volume of 400 neurons over there is what is connected down to 120 neurons, and this is a fully connected thing. So, all the 400 neurons go down to 120 neurons. Subsequent to that is a very simple connection which is 120 such neurons which are linearly connected, and then again subsequently linearly mapped onto 84 neurons, and from 84 neurons we go down to these 10 neurons, and these 10 neurons are basically the final neurons in the classification which are present over there. Now, following that, the next part which we were defining is my forward pass of it. Now, you can see that we have written down some extra lines over here as a print statement, and the whole reason for writing this print statement was actually to pull down and probe out what is the size of the output coming down from each of them. Okay. So, you have your first layer of convolution. So, if I give down a 28 cross 28, then what comes down after my first layer, then what goes into my second layer. So, after the max pooling and everything is done. So, this was just to write it down. However, when you are writing an actual function over there, you can pretty much do away with writing these prints over there. It is just going to flood out your whole zone. It does not have any other significance when you are doing the main training. So, in the next lecture when we are going to cover down the actual model and then train it down. So, you will see that these print statements are out over there. So, here to go down by simple, what I have within my forward definition is that I have some input x which is taken over there, and then the first pass is that I do a convolution with as per what is defined in conv 1. So, now conv 1 was what is defined over here, and that is a 2D convolution of using kernels of size 5 cross 5, and there are 6 such kernels which happen. So, what comes down over here is then passed on to my max pooling, and my max pooling is defined over here, which is pool 1, and this max pooling is just a 2 cross 2 max pooling present over there. So, the number of output channels still remains the same. Now, that is what I print down over here. Now, you need to keep something in mind. So, over here the number of output channels is 6, over here the number of output channels is again going to be 6, and then you do a convolution and get down a number of output channels equal to 16, and then you do a max pooling, and here also you end up getting at 16, and then finally you would see that whatever is the size over here, that would come down as 16 into 5 into 5, and that is equal to 400 neurons. Now, those 400 neurons are what are invoked over here, and then the next part is basically to so this what I am doing technically over here is that in the earlier case you had a volume where you had 16 channels and you each had a size of 5 cross 5, but then I will have to arrange them into one single set of neurons so that I can have my fully connected layer being called out. So, the whole purpose of this command of view is basically to flatten it out or minimize it down to one single dimension over there. Now, once that is minimized, then you do your transfer function. So, pretty much you can do your transfer function before you try to minimize, or even after that, that does make much of a change onto it, and then you have your fully connected layer going down. Now, once your fully connected layer is connected, so you have your from FC1 the total number of output is 120, which comes down over here. Now, you connect down your FC2, which will take in 120 neurons over here and map it down to 84, and then you go to FC3, which comes over here, which maps down 84 neurons onto just 10 class of neurons, and finally is the output to be returned over there. So, this is what becomes my function definition and my forward pass definition over the whole network. Okay. So, once that is done, let us try to actually invoke the network and try to print the whole network. So, if you look into this, this is what comes down as my network. So, let us zoom out a bit so that we can see. Yeah. So, the whole network comes down in one line. So, you see that my model is what is called as LeNet, and because that is how I had defined it over here, my class is called as LeNet. Now, within this network, the first one is a convolution of 2D, that is what corresponds to my structure of conv1 on the first level. So, it is a 2D convolution which maps down one channel to 6 channels with kernels of 5 cross 5 and a stride of 1 cross 1. Now, by default I had not actually defined down what my stride over there was, and as such it takes down a default stride of 1 in case of convolution, as well as I had just mentioned down my kernel size is equal to 5. If I had mentioned down say kernel size is equal to within brackets 5 comma 10, so that would mean that the x size is equal to 5 and the y dimension is equal to 10. So, you can have rectangular kernels as well, as we had discussed in the earlier class, any generalized kind of a kernel, and it becomes easier. However, since we are just sticking to writing down only LeNet, so we are not making any change over there. Okay. The next part is you have a max pooling of over a kernel size of 2 cross 2 and a stride of 2 comma 2, and then sort of what is also called as a dilation of 1 comma 1. Now, the whole purpose over here for this max pooling, as you see, is quite simple. So, the whole job is just to get down a strided max pool coming down. Now, in case you had meant down this stride as 1 comma 1 or just going up over here when you had defined this stride as 1, then you can have down something similar to just a maxima operation over a space, or what is also called as a gray level dilation over there. Now, this particular instruction over dilation of 1 comma 1 is something which is given down to actually instruct the code that in case there is a parity mismatch at the borders, then how much of extra padding you can do so that your operator works it out. Now, that has a relationship with the stride itself. So, if the stride was larger, then your dilation, allowable dilation, would also be going down higher. Now, for all general purposes, if you are sticking down to using a fixed size of the image and your image sizes are defined in such a way such that all of these are integral, then you might not even have a residual dilation added down at any point of time. Now, comes down the second part of it, which is the second convolution. So, my second convolution is what maps down from 6 to 16 kernels, and then via a kernel size of 5 cross 5 and a stride of 1 comma 1. Okay. Then I have my max pooling. Now, pretty much like whatever is the size of the output which comes from this. So, after my convolution 1 and my pool 1, whatever is the size of my output, I could have sort of achieved almost a similar sized output if I was giving down a stride of 2 comma 2, as we had discussed in the earlier class. However, the problem is that there are significant differences in using just stride versus just using a max pooling over there, and it has been found out that with strides you tend to lose down on higher frequency components, which you can actually preserve down in max pool. So, down the line as you go on, so if you have very small objects which are very significant, but then they might be at a risk of getting eroded out because of the resolution problem, just by putting down these max poolings, you are still going to reserve and keep all of these objects and structures quite popularly preserved across the whole depth of the network as output comes down. Now, till here it becomes okay, and then the next part is where you have to connect down your linear neurons. Now, this comes down from this definition over here, which will assume that after this the output is somewhat made flattened and coming down to 400, and that is how it is connected. Now, since that is not part of a network as such, but it is just part of some data processing operator which we have, and for that reason this view is incorporated only within the forward pass. So, similarly say ReLU or these kind of transfer functions which are not to do anything with the memory to be taken down within the network or within the data pipeline over there. So, they are just transfers over the data, they will just be operating over the data and then making a change to the nature of the data. So, you do not have them within the network itself, but they just come down within your forward pass definition. Okay. So, you do not see them in the network architecture. So, just trying to print down a network might not always end giving you exactly what is the nonlinearity or the transformations which come down over there, and you have to be really clever. So, one way is like you can actually fool down somebody by just giving them this network and then without having said about the rest of the stuff. A lot of people do practice it, but please do not do that, rather define everything in the full possible way, so that it becomes a reproducible kind of a work. Now, having said that, the final part over here was just 10 neurons over there, and what you get down at the final part is just a classification of some sort. Okay. So, we do not have any sort of a linear, any sort of a nonlinearity in terms of a tan hyperbolic or sigmoid which is given down over here, but it is just what comes down over there, and that is what the network has to learn out. Okay. Now, let us do a feed forward operation over there. Now, in this feed forward operation, what the whole objective is that I have my inputs of, so here what I am taking down is 32 cross 32 to be conformal with my LeNet. Okay. Now, because there they were not taking down 28 cross 28, but you had patched it out so that you do not decay while that by the time you reach over here. So, I just create a small dummy variable over there in terms of a tensor which has 32 cross 32 spatial span. I have one gray channel present over here, and this final one is what is called as the batch size. So, in the last week's lectures when we were doing advanced learning techniques with different kind of learning algorithms, so either it can be an epoch update or a batch update or per sample wise update. So, this is what would define down over here. Now, the good thing with convolutional neural networks is that they are really designed to optimize over here across the batch. So, when you are passing down a batch, it is not just one sample by sample which is going through it, but it is as if the whole tensor gets processed out over there, and based on the whichever index of the tensor you are looking down, it will be making a modification. So, that also brings us to another challenge, is that if I just write it down as a torch.tensor 1 comma 32 cross 32, so that would assume this first index to actually be the batch number and the next two indices to be what is related to the data. Now, the problem which comes down over here is that my input has to come down in a form as the number of channels and the spatial span of the data over there. So, if my number of channels are not defined, then it makes it hard because I have a 2D convolution. So, in that case I will have to have my x span and my y span which is given down over here. This has to be my number of channels and this has to be my batch size over there. So, even if you just have a grayscale image, you still have a, you will still have to represent it not as a 2D matrix, but as a 3D matrix, where the third index in the standard case is equal to 1, and here it's the other way around of indexing. So, the lowest order index, or say in if you have a normal 2D matrix given down in your Python NumPy or SciPy, then you have your x axis which is your first index, then your y axis second index, then z axis which is your third index. Now, here we write it in the opposite way, where my x axis is my last most index present over there, then comes down my y axis, then comes my z axis, and then comes down my batch number over there. So, if you are doing 3D convolutions, you will just have an addition over there, and then that is how it goes down. So, when we come down to them in later on lectures, you will find out how we define around that, but this is really critical. I mean, for your CNNs, this is one of the main problem which a lot of people would otherwise end up doing over here. So, once we have defined this whole thing and casted that as a variable, my next job is actually to get whatever is the output over there. Now, when I do that, you see a lot of these things which get printed over there, and that is sort of the size of the output which comes over there. The whole reason was that what I had done is we had these print statements given down over here, and they were just printing out the size of each of these variables which comes on the output over there, and that is what we are printing out over here as well. So, for convolution 1, you see that it produces a torch tensor which has a size of 1 comma 6 comma 28 comma 28. So, you had a 32 cross 32 image of one channel, you convolve it with a 5 cross 5 kernel and 6 of those unique kernels over there. So, your total number of output is going to be 6, that is okay. My batch size was 1, that is the batch size which I am getting down over here. Now, comes to my spatial span over there. So, my spatial span is something like I had 32 minus 5 plus 1. So, that makes it 28 and divided by the stride, which is equal to 1 itself. So, it still stays at 28 comma 28. Now, after that when I do my max pooling, so that is a max pooling over a 2 cross 2 window and with a stride of 2. So, that is where my number of channels is still going to remain the same, and my x span and y span, or the x and y directions, the size is going to reduce to half of that, and that is what I exactly see over here. Next, what I do is I do a convolution with the second convolution operator, and my second convolution operator, if I go up here. So, over here my second convolution operator is what maps down 6 channels onto 16 channels over there, and with a kernel size of 5 comma 5 and a stride of 1. Okay. So, what I am essentially doing down over here is that I have mapped down 6 channels onto 16 channels. So, the output over here will be having 16 channels. Okay. Now, my batch size over there is still going to remain 1, because I just have one batch of an input data given down, just one single input data in a batch which has been given down. Next comes down my result of the convolution. So, add a 5 cross 5 kernel over there, and then my input to this convolution layer was of size 14 cross 14. So, that makes it 14 plus 14 minus 5 plus 1 divided by 1. So, it is 14 minus 5 divided by 1 plus 1. So, that whole thing makes it down to 10 cross 10. So, that is the output which comes over here. Then comes down my next pooling layer, and that gives me 1 comma 16 comma 5 comma 5. So, you see that the total volume which comes down over here. So, you have on one side you have your batch, which is as of now size of 1. So, in case it was batch of 10, then you would be seeing down 10 coming down over there. So, I can actually change it down. So, in case say I just make a modification over here and then write it down, you would see that this batch size of 10 comes down over here. Now, what you need to remember is that the resultant over here is for each batch itself, it is a volume of size 16 comma 5 comma 5, that is 400. So, in the earlier case, when I just had one sample in my batch, or my batch size of 1, then it was just 1 comma 16 into 5 into 5, that was my whole volume which was being created over here. Now, that I have 10 over here, so that is 10 such samples, and then 16 into 5 is what is created. So, that is equal to 400, and then what I do is I look into the flattened response. So, my flattened response over there is the same as batch size and the total number of neurons in that volume, which is 400. So, that goes down from my result over here, where I am just doing a flattening using the view function. Okay. Now, after that I have my fully connected layers connected down, which connects down 400 neurons to 120 neurons. So, that is the output. Then those 120 to 84 neurons, and then 84 neurons onto 10 neurons. Okay. So, this is what is to look down as how the data behaves as we go through over here. The next part is to also try to investigate down what is the total number of parameters, because in the last class we had decided that what is the total number of weights which each of these kernels would be learning down over there. So, the total number of weights is dependent on what is the total number of input channels and the spatial span, and these many times like this quantity time into the total number of such unique kernels you are going to define in one particular layer. That is the total number of parameters which comes from. So, this is a small script which is written down to recursively actually traverse through the whole network and actually find out the total number of parameters per layer, and then find out to the next one. Okay. So, in the first one, what I have is basically in the first layer, which is basically a convolution layer. So, I have one such channel which is mapped out to 6 channels and via a 5 cross 5. So, this is my weight space which gets created over there. So, there are 6 such kernels where each kernel's size is 1 comma 5 into 5. Okay. So, that is a 5 cross 5, and my z direction over here is just 1 because the number of input channels. So, there are 25 neurons which come down over here, and then you have this 6 of them being created. Okay. Now, the next part is that corresponding to each of these convolution kernels which you have over there, you will also have a bias function, whereas the resultant of convolution is basically you convolve or do a dot product with the whatever is the input over there, and then you offset it with the bias function. This is what comes down. So, since there are 6 such unique kernels which are to be computed out over there, so each will be associated with its own bias function, though there are 6. So, over here my total number of weights which I learned down is 6 into 1 into 5 into 5 plus 6. Okay. Now, in the next case what I have is from 6 channels I map down to 16 channels. So, each kernel over here is going to be of the size of 6 into 5 into 5. Okay. So, that is about on the volume side, so while it has a spatial span of 5 cross 5, on the volume side it has a span of 6 such channels. Okay, and there are 16 such unique channels which result out over here. Now, along with these 16 channels, so there will be 16 such bias functions as well, which will connect down to give an offset, and that is why you get down 16 biases coming down over there. Now, once this part is done, then what you have is 400 neurons which are flattened out and they connect down to 120 neurons. Now, 400 to 120 neurons is pretty simple, it is 120 into 400 what you have done. Also remember that corresponding to each of these neurons in the first hidden layer which have 120 neurons, there is also a bias. So, there will be this 120 biases which also need to be added. So, going down by the same argument, 120 outputs over there from the previous layer is what connects down to 84 neurons, and for that reason you also have 84 biases which comes down. Then 84 neurons connect down to 10 neurons, and then you have 10 biases which comes down, and then if you do this multiplication and then the summation across each of them. So, multiplication of number of weights in each layer is multiply all the indices over here, then sum down by multiplying it with the next layer. So, in the next layer it is just 6. So, this whole thing plus 6, then the product of all of these numbers plus 16, then the product of all of these numbers, then plus 120, then product of all of these numbers, then sum it up with 84, and that is what you do, and finally you get down this is the total number of learnable parameters. So, you have within a standard LeNet 61,706 such learnable parameters, or the number of weights which will have to be tuned. So, this is pretty straightforward. Now, you might ask me a question that does it depend on the batch size? No, it does not depend on the batch size in any way. Let me do a very simple trick over here. I will change it back to 1 and just run this part. So, now you see the batch size has changed, and now let us run this part over here as well to look into the number of trainable parameters. See, the number of trainable parameters does not change because each weight is not dependent on the batch size or the total number of samples which goes into it. So, that is just for my processing part over there, how to optimize and speed it up. Beyond that, it does not have a physical significance on my total number of parameters in any way, and so do not get confused around with batch size in any of them. So, this was about getting you introduced to LeNet and trying to get you into the nitty gritty of how it is defined and how the data passes through it and how you can look into it. So, in the next lecture what I am going to do is to run down the whole trainer module over there, train it over time, and review of what was there within the architecture, and then what was the kind of weights which it had learned. So, we had done those beautiful weight visualizations for fully connected networks, but then within a CNN, because these are now convolutional weights. So, then how do they look like? Is this something to be really amused and intriguing thing to look into it? So, till then stay tuned and we will get back.